Hello, everyone. Thank you for coming to this session. So today I want to talk about 3 JavaScript auth architectures and how secure or insecure they really are. Now, auth is hard, and a lot can go wrong. But many of the challenges that developers actually run into when they're doing auth aren't necessarily the things they were initially the most anxious about. We worry about things like user management and compliance and security attacks, and then end up struggling with where to store tokens and frustrating CORS errors. So the way that your app is architected has a huge impact on auth and on all of these concerns. But before I get too deep into the architecture, I want to do just a little bit of quick terminology. So authentication is the process of proving you are who you say you are, that is, logging in. Authorization is the process of granting or denying access to resources, like whether the user has permission to access an API. An authorization server is a server with endpoints for issuing authentication and authorization credentials in the form of tokens. An authorization server issues ID tokens to identify authenticated users, access tokens to grant access to APIs, and refresh tokens to renew a user's access token before or after it expires. So let's talk about auth architectures for browser-based JavaScript apps that are downloaded to and run in the user's browser. This includes things like single-page applications and statically generated sites. Now, your architecture might look something like this. You might have a traditional backend serving your browser-based app in the front end with a server, a database, and an API. Or you might have something like maybe a Jamstack app running on a third-party platform as a service, like Vercel or Netlify, with serverless functions and maybe a SaaS provider or two. Or you could have any combination of complex or dynamic architecture components. So I want to compare the security capabilities in a traditional backend app versus a browser-based front-end app. The backend is a confidential client, and it can authenticate itself with the authorization server using a secure client secret. It can safely store, manage, and revoke user sessions. And it can also safely store sensitive tokens on the server or in HTTP-only cookies, which can only be created and read in the backend. On the other hand, an app that runs in the browser is a public client. It can't authenticate itself with the authorization server using a client secret because it has nowhere to safely store this. It can't locally manage user sessions since all data in app memory is lost every time the app is reloaded. And any place that it could store tokens is accessible to cross-site scripting attacks. So the security implications here are definitely not trivial. But if you control a backend that serves your front end, then a backend for front-end architecture is a secure way to implement authentication and authorization for browser-based applications. Let's say you have a front end, a code executing backend that serves the front end, and an authorization server. And you need to implement OAuth 2 for authorization and OIDC for authentication. Now, in a backend for front-end auth architecture, all of the auth flows take place in the confidential client. The front end has no need to persist user session data because all of that is managed in the back end. Now, access and refresh tokens in this case never even touch the browser. The back end for front end is a proxy for all auth processes that the front end app wants to carry out in order to authenticate users and authorize access to resources. So here's how this actually works. An unauthenticated user loads the front-end application, which calls the back-end auth API to check for an existing user session. The back-end, upon verifying that the user doesn't have a session yet, creates a proof key for code exchange or PKC challenge. This means that it generates a cryptographically random string called a code verifier. And it then uses a hashing function called a code challenge method to hash the code verifier to create a code challenge. Now, hashing is irreversible, so once a string is hashed, we can't do any processes to that string to get it back to the original input. Now, the backend then sets a cookie in the user's browser containing the code verifier and the code challenge. The PKC cookie ties this user to their PKC challenge, which isn't stored in the backend yet because the user session is not going to be created until we have a successful authentication event. The cookie is HTTP only, which means it can't be read by JavaScript in the browser, so the front end and any malicious actors can't access its contents. When the user clicks the login button, the front end is going to send a request to the backend Auth API's login endpoint. The backend composes an authorization request with appropriate configuration and then redirects the browser URL to the authorization server's authorize endpoint with the user's code challenge and code challenge method included as parameters. The user is going to enter their credentials, and the authorization server verifies these credentials and then redirects to a backend auth callback route with the authorization code in a query param. The backend then makes a post request to the authorization server's token endpoint with the client secret, the code, and the code verifier. And the authorization server verifies the client secret. It verifies that it did indeed issue the code, and it uses the code challenge method that it received with the authorization request earlier to hash the code verifier and then match this freshly computed code challenge with the code challenge that was sent by the backend with the initial authorization request. The authorization server then responds with an access token and refresh and ID tokens if they were also requested. The backend can then delete the Pixie cookie, and it creates a unique session ID and then stores the tokens in a session object. The session's time to live should be set to match the refresh token expiration. The backend sets an HTTP-only session ID cookie in the user's browser. And the backend then redirects the front end to a login callback page, which can perform post-login logic, like setting the login state and possibly redirecting the user. Now, every time the front end app initializes, it should call a backend check session endpoint. And this request includes a session ID cookie if it exists. The backend uses the session ID to look up the user's session, and then if the session exists and the access token is valid, then the backend can use the access token's expiration to schedule a proactive refresh grant right before the access token expires in order to ensure a seamless user experience. Now, if the access token is expired, but the refresh token is valid, then we can perform a refresh grant by sending the refresh token to the authorization server's token endpoint. The authorization server responds with fresh tokens, which are then saved in the user session. When the app needs user info, it can call a user info endpoint on the backend with a session cookie. The backend looks up the user session, and then it can either decode the ID token to get the user info, or it can send a request to the authorization server's OAuth2 user info endpoint with the access token in the authorization header. The auth server then returns user info, which can be stored in the user session and sent to the front end. Now, you should use this method if the user's data is likely to change during their session in order to ensure that we're always fetching up-to-date information, since the contents of the ID token are not going to change unless new tokens are issued and acquired. Now, if a user loads the app and the check session looks up the session ID to find that either the session and the refresh token are expired, there was no cookie attached to the request, or the session doesn't exist, then the user's not authenticated and they're going to need to log in. Now, let's say the user is logged in and they do have a valid session, and they need to access data from an external resource API that requires authorization. The backend for front-end proxies external API requests since the front end doesn't have an access token. The front end is going to make a request to the backend proxy API. Get is used as an example, but it could be a post request with a body. And this request includes the session ID cookie. The backend uses the session ID to look up the user's session. And then the backend proxy API forwards the request to the resource API with the user's access token in the authorization header. The resource server validates the access token, and then it can return data. And the proxy API then forwards the resource server's response to the front end. Now, if you have a local resource API that lives on the same domain, then the front end can call this API directly using the session cookie, looking up the session, and validating the stored access token, and then returning data to the front end. Now, when the user wants to log out, they click the logout button, and the front end makes a GET request to the back end's logout endpoint, and it includes the session ID cookie. The back end looks up the user's session and then redirects the browser to the authorization server's Auth2 logout URL. The authorization server logs the user out, then redirects to the back end logout callback route. The back end removes the user's session and deletes the session ID cookie, and then redirects the browser to a front end logout callback page where the front end can then perform any post-logout logic, like redirecting the unauthenticated user. So backend for front end is a fairly complex architecture, so let's review its pros and cons. It is the most secure way to perform auth for browser-based apps because auth takes place in the backend confidential client. Same-site cookies prevent cross-site request forgery, or CSRF, as long as the true backend for front end pattern of one backend per front end is being observed. The architecture is also highly customizable to suit different security needs. Tokens are stored in the confidential client, which prevents token theft and abuse through malicious JavaScript or browser storage access. And attackers can't use malicious JavaScript to execute a silent authorization code flow to abuse the user's session in order to acquire the token. And since the tokens aren't exposed to the front end, attackers can't acquire and exploit a stolen refresh token in order to perform an illegitimate refresh grant. Now, the biggest trade-off to using backend for front end for auth is that the architecture is complex. It requires backend infrastructure, whether that's your server with code with a backend that can execute code and a data store, or serverless cloud functions, or some kind of a hybrid approach. And as you saw with the external API example, cookies only work on one domain, so cross-domain requests need to be proxied. It's also just a fact that building a proxy API is more work than directly calling the API from the front end. And backend for front-end auth can have a fairly significant barrier to entry that often requires you to have a solid understanding of OAuth 2 and OIDC standards and their implementation. Finally, backend for front-end is so specific to your particular app and your APIs that varying degrees of manual implementation are going to be required even if you are using an auth provider. Now, a few identity servers do provide a hosted backend for front end out of the box for free. This is the default approach in one provider, which is FusionAuth, because the authorization server itself is downloadable and can be run as an integrated component of your application architecture. So this brings us to the second architecture, which is a token mediating backend. Now, token mediating backend auth architecture is similar to BFF in that it manages auth in the backend, but it differs because although it doesn't store refresh tokens in the browser, it does use access tokens in the front end. Now, token mediating backend still uses authorization code flow with Pixie. It still stores a session on the backend, and it uses a session cookie with a check session endpoint to look up the user's session. The Auth API then, however, responds with an access token, and it delivers this access token directly to the front end, and the front end can store this in app memory. Fetching user info works pretty much the same way as it does in BFF, with options to either decode the ID token or request user info from the authorization server. And when the front end needs data from the resource server, it actually calls the API directly, authorizing that request with the access token in an authorization header. The API then validates the token and returns data directly to the front-end application. Now, if the access token is expired or invalid, the API is going to return a 401 unauthorized error. In response to the 401, the front end calls a back-end auth API to get a new access token using the session cookie. The backend then looks up the user's session, and if the backend has been keeping the access token refreshed using scheduled proactive refresh grant, it can send a response with the up-to-date access token. The front end can then use the new access token to fetch data from the resource API. Alternatively, you could preemptively request a fresh token from the backend before you call the resource API. And you can also fetch data from local APIs with the authorization header and the access token, or with the session ID cookie. Finally, logout works the same way it does in backend for front end. And in many ways, token mediating backend is similar to backend for front end and shares some of the same benefits. So auth flows take place in the backend. The part of the architecture that manages auth flows is a confidential client. Same-site session cookies prevent cross-site request forgery. And this architecture can also be customized for advanced security. Refresh tokens are stored in the confidential client, which prevent theft and session abuse via malicious JavaScript or browser storage access. And the front end can interact with resource servers directly without having to proxy API requests through the back end. Now, several auth platforms use token mediating backend as the default approach in their JavaScript SDKs, managing sessions on their servers, but then delivering the access token directly to your front-end client. So some of the token mediating backend trade-offs are similar to backend for front-end trade-offs, but with some additions. If you're building the token mediating backend yourself, the auth part of the architecture is still complex. You don't need to manage proxy resource APIs, but you do still need a code executing backend infrastructure. And you also need a strong understanding of OAuth 2 implementation and best practices in order to build the token mediating backend. Access tokens are received and sent in the browser, and they might also be stored in app memory, which does expose them to theft and abuse through cross-site scripting, granting an attacker access to the user's resources. So you do need to take measures to prevent this by doing things like binding the token to the client. Now, you may need to build a token mediating backend yourself, but the most common place that you're going to see this pattern is with SaaS auth platform JavaScript SDKs, because they can host the auth proxy, but they live outside your infrastructure. Finally, token mediating backend requires additional security, which I'm not going to get into now, but you can check out this article for more details. And this brings us to the third architecture. And this is the browser-based OAuth 2 client, wherein auth takes place entirely in the front end. These apps don't rely on any backend services, and this architecture is also the least secure option for browser-based apps. This time, we have a front-end app, and we have an authorization server. A browser-based OAuth 2 client architecture must use PXE to protect against CSRF and authorization code injection. Session management isn't proxied, so everything happens directly in the front-end app. And we can only store tokens in memory. We should never put them in browser storage. So given all of these things, please understand that browser-based OAuth 2 client is not a secure solution. Without a backend, the client can't authenticate with the authorization server using a client secret. We can't store tokens safely anywhere, because backends can set HTTP-only cookies, but frontends cannot. So refresh tokens can't persist through a browser reload unless we resort to unsafe storage mechanisms. Refresh and access tokens are in app memory, and as we already covered, that makes them vulnerable to theft. So BBOC should really only be used when an app uses auth for convenience, but not for security. So you might say, like, why the heck would I even do that? Under what circumstances would that happen? An example might be like a gaming app that shows usernames on a leaderboard, or an app that uses public recipe APIs to compile meal plans, or link sharing apps like URL shorteners. These types of apps can be used anonymously, or they can save data, but the data is saved for convenience, and they don't contain any data that you would care if it got stolen. So when the user arrives at the application and clicks the login button, an auth service runs a login function that creates the PXE challenge, and that can be stored in session storage in order to persist the challenge through the redirect to the authorization server during the authorization request. The login function generates the authorization request with appropriate configuration, which redirects the browser to the authorization server's OAuth 2 authorize endpoint with the PXE code challenge and the code challenge method. The user enters their credentials, and the authorization server authenticates the user. And the auth server then redirects the browser to a login callback page with the code in the query params. The login callback page then makes the post request to the authorization server's token endpoint with the code verifier and the code. The no client secret can be sent in this case because client secrets can't be stored securely in a public client. The authorization server verifies the code, it hashes the code verifier, and then it compares the code challenges. And if all of that goes well, then it responds with tokens. The PXE challenge is deleted, and tokens are then stored in app memory. Now, the auth service can use the access token's expiration timestamp to schedule proactive refresh grant. But I want to pause here to talk about security again. This is the least secure architecture, so several things need to be done to minimize risk. Don't store access tokens or refresh tokens in browser storage like local storage. Access tokens should expire in less than 60 minutes, but ideally closer even to 5 to 10 minutes. And this is one reason that proactive refresh is very important for a good user experience. Refresh tokens must be single use, meaning once they've been used one time, they need to be revoked. And they also need to be rotated. So every time a new access token is issued, a new refresh token must also be issued, and the last refresh token needs to be invalidated. The new refresh token, however, should still expire in the same time that was left on the initial refresh token rather than extending that amount of time. And these are all settings that you should be able to set up and configure in your authorization server. On the other hand, ID tokens are intended for the client, and they can be decoded in the front end in order to populate profile info. Alternatively, you could call the authorization server's OAuth 2 user info endpoint to request up-to-date user info, like we did in the previous examples. And then to fetch data from a resource API, the front end sends a request to the API with the access token in the authorization header. The API validates the token and returns data to the app. When the user clicks the logout button, the app's going to run a logout function that redirects the browser to the authorization server's OAuth 2 logout endpoint. The authorization server logs the user out and revokes tokens, and then redirects the browser to the app's logout callback page. They then can redirect the user appropriately within the application. And since app memory was cleared on the redirect, the user is now logged out of the front end. So now we've come to benefits and trade-offs for browser-based OAuth 2 client architecture. The first benefit is it can be serverless. There's no dependency on a code executing backend. It's much less complex compared to backend for front-end or token-mediating backend. And a few auth providers' single-page app SDKs default to this approach in order to keep their SDKs easy to use and to minimize latency issues. Finally, the app can interact directly with APIs that live on any domain. When it comes to trade-offs, I think I've mentioned enough times that this is the least secure approach to auth for front-end apps. Public clients can't securely store client secrets, meaning the app can't authenticate itself with the authorization server. This can allow things like client impersonation attacks, so it's very important to use PXE and to use exact string matching in redirect URIs. Tokens in the front end are vulnerable to cross-site scripting, and refresh tokens shouldn't be persisted in the browser. So that means reauthentication on refresh is going to be required. Now, the security risks make this approach unsuitable for apps that need basically any security, like business-critical apps or financial apps or any app that contains personally identifiable information. Now, there's a whole set of best practices for making browser-only apps less insecure, and I mentioned a few of them, like short-lived access tokens and refresh token rotation, but there are many more, so none of them actually completely prevent token theft in this architecture. So now that we know the auth lifecycle for each architecture, we can choose the right one based on our own security needs and infrastructure. Backend for frontend is the most secure and is the recommended architecture. So you should always use backend for frontend if your frontend runs on a server and a code executing backend. You have same domain APIs, strong security requirements, or you're storing business critical or personally identifiable information, and or you need to make authorized calls to external APIs. Now, you really should use backend for frontend if you have control of your backend. But you can consider a token mediating backend if you have a similar architecture to backend for frontend and your system requirements prevent proxying APIs. So examples of this might be apps that need extremely low latency, like streaming apps or real-time collaboration tools, or apps with compliance or direct communication requirements for things like payment processing. Finally, many SaaS identity providers use a token mediating backend out of the box because they can host an auth proxy to manage sessions, but they can't provide same-site cookies for your API because they live outside your domain. Now, you would need a plan with custom domain support, and even then, most providers don't support backend for frontend out of the box. You would still need to build the auth proxy yourself using their APIs. A browser-based OAuth 2 client is really not recommended due to its insecurity. The specification straight up says it doesn't recommend it, but you could use it if your architecture prohibits backend control, if auth is used for convenience, not security, if you need to access cross-origin APIs that are public or maybe don't need API access. Now, you can check out full code demos of these architectures on GitHub at this repository, as well as a fourth demo which demonstrates using a free out-of-the-box hosted backend for frontend. Now, if you recall, this talk is about 3 app architectures, but more accurately, it's 2 secure architectures plus 1 that's insecure. And it's important to understand the security implications in each case. If you read your auth provider's documentation thoroughly, you'll probably be able to recognize these patterns. So my name is Maida. I am the Senior Director of Developer Relations at FusionAuth, which provides developer-first downloadable auth APIs, as well as the hosted backend for frontend. And you can connect with me on social or by scanning the QR code. And to learn more, the architecture demos are on GitHub, and I have actually created repos for these in both React and Angular, so pick your flavor. And you can check out some of these additional standards resources if you really want to dig in. I also make miniatures and artisan keycaps for mechanical keyboards, and I design custom stickers. So please come talk to me, find me in the hall if you have any questions about auth or if you just want stickers. And I'm grateful that you chose to spend your time with me today. So thank you very much.